If I type now the power per unit of area, the power arriving in the table here, in an energetic, I'm speaking about irradiance, watt per square meter. But photometry, I have two kinds of quantities in, in that definition. One is the illuminance, how much light arrives to the used surface, and this is measured in lumen per square meter and has a specific name, lux. Or if you take that lamp, you cannot consider that is point source. It has a surface and the flux is coming out from the lamp. When you look on the lamp, you have another quantity that is called the excitance. And
is measured in lumen per square meter, and we don't use the unit lux for that kind. Two different things, you see. Photometry is more specific than radiometry. And the last one, the power per unit of solid angle and surface. What is arriving in the screen, for example. This quantity is very rarely used in photometry. It is a no-name quantity. We can measure, of course, in watt per square meter and steradian, but I remind you that is what penetrates in our eye. It is measured in lumens per square meter and steradian, but lumens per square meter, per steradian, sorry, is the candela, is candela per square meter, and in European literature, you can find also the unit nit, NIT, or if you go to American, you speak about foot candelas. That means candelas per square foot, okay? This is the luminance. Why luminance is important? In fact, it's the quantity of light that is reflected from the screen arrive to my eyes, and the pupil size define the opening of the eye and how much light will be collected and illuminate my the retina inside. This is because luminance is penetrating the eye. One by one, curious that what happened here. Sorry, one slide is missing. How we measure the luminous flux? The luminous flux, we measure it by putting a light source inside that we call an integrating sphere or an Ulbricht sphere. The lamp has to be 10 times smaller than the dimension of the sphere. The sphere is completely reflecting. We have to know very well what is the reflectance of the source of the sphere at any point if we want to make metrology. And then we can collect the light thanks to a calibrate photocell, and if we take a small amount of light, we can measure here, for example, a number of volts, and this number of volts, if the sphere is calibrated, correspond to a number of lumens. Why? Because if you put the lamp in a big sphere, the fact that the light is inter-reflected inside the sphere, you transform the system like if you had a mathematical point in the middle of the sphere that emit all the light to a uniform way in 4p space. And then if you take just a small amount of light, just to multiply by 4p, and you have the lumens. The luminous intensity is the ratio between the flux toward a direction defined by the solid angle. In reality, it's the element of the flux over the element of the solid angle, and the d omega should tend to 0 normally. And this is the definition. And you can see here we measure in candela. A light emitting diode, a red one, that just show you that a device is switched on or off, is 0.05 candelas, very small. A candle, by definition, is one candela, because it was the first standard of candela. We'll speak about that. 100 watt incandescent lamps is 150 candles, 150 candelas. That because my grandmother told me I want 150 candelas lamp, it's the same. A lamp, the headlamp, high beam for the cars, if it is incandescent lamp, is something like 100,000 candelas. And if we speak about LEDs or even now laser lighting, you add most probably 10 here. A lighthouse for marine use, 3,000 candelas, and a flash tube, even the flash of your mobile phone when you take a photo, instantaneously can reach 1 million candelas. The sun is 1 billion candelas, is at least 3 orders of magnitude higher that we have here. This is why if you look the sun for a long time, you may be blind even for the rest of your life. Well, candela is very important. Candela, the definition is here. Candela was one of the 5 fundamental units defined in SI, the International System of Units. Second for the time, meter for the distance, kilogram for the mass, ampere for the current, and candela for the light. Since May 2019, if I'm correct, this definition of SI is obsolete. We no more use the International System of Units using 5 units, but we switch to a definition based on 7 universal constants that our metrology, national metrology labs, they know to measure with a very big precision. What are those fundamental units? Speed of light, charge of electron, Planck's constant, Boltzmann constant, Avogadro constant, yes. One is missing. And the 7th, who replaced candela, is simply this value, 683. This is not measured by definition. It makes the link between lumens and watts. It was a big question why keep candela or the 683 constant inside the new definition of the system. This is because the candela is the only, and the 683 is the only fundamental unit that relates to human being. All the others, they are completely independent of human beings. If one day dogs can measure current, they will use the same definition, but if one day dogs want to measure light, they cannot speak with the same units. Okay? Well, and to be more precise, candela was the very first standardized unit. Candela has been standardized in the middle of 19th century and has been standardized as the light that you get from a stearic candle produced in UK, in England at that moment, and that candle has to be visible at 2.5 something miles around in flat space and with good weather. That was the first definition of the candela. That because one candle equal almost one candela today. Then end of 19th century, we switched from the candle to a incandescent lamp. Later from incandescent lamp to other kind of discharges. And today we completely dematerialize the system. We use that definition that can be measured with very good precision. But historically speaking, candela exists as standard before any metrology system. And when they integrate candela in the new metrology system SI, they went in obligation to calculate this constant 683 in order to make the link. How we measure the luminous intensity? This is much more complex, because to measure the luminous intensity, if you have a lamp, you have to measure the light coming to all directions. And to do that, you use such kind of instruments that we call the spectrogoniometers. And this instrument has to be at least three times bigger than the lamp. Usually, this part here is 3 to 4 meters. The lamp is in the middle, always oriented down, and you don't have to move the lamp, because if you move the lamp, you change the air circulation condition, and you can change the temperature of the lamp, and you can change his behavior. That means the moving part is a mirror in 3 meters further that send the light somewhere to a calibrate radiometer, and you can scan the system. All the system has to be in a black room without parasitic light, with stabilized temperature plus or minus 0.1 degree, with stabilized humidity. Well, an instrument like that plus the building equal several million euros or dollars, multiplied by 100 in rupees. This explains why such kind of instruments, when they are especially calibrated, you can find 3 or 4 per country, no more. Usually the central calibration labs they have, otherwise you have, in many countries you have 0. You have to rely to other countries for getting these measurements. An integrating sphere, like that I showed you before, independent on the size. In my lab I have one that is 1.8 meter diameter. This one can cost around 10 to 20,000 euros. If you want now for your students, it's very easy to build for almost 0. You take Felisol, you know, the plastic, the white plastic balls, and you can use it as an integrating sphere. You make holes, and it works very well if you calibrate it. For students, it's enough. And this device measure that we call the photometric solid. It gives you the distribution of the intensity in all directions with a minimum step of 5 degrees per direction. Make a single measurement of a lamp takes a full day, and a measurement of like that in Europe, in a accredited lab with such instruments, you will pay 2,000 to 3,000 euros to measure one lamp. Only industry can pay things like that. Illumination. Illumination is the ratio between the flux in a surface divided by the surface, and more precisely dF over ds is a differential equation again. Some orders of magnitude. Summer at noon in the sun, and I will say when you have white sand outside near equator, more than 100,000 lux. Under overcast sky on a street between 200 and 10,000 lux. Behind a window, not very far, under 1,000 and 3,000 lux. The night with full moon, 1/4 of lux. But we still see very well, and we consider that it's very romantic. In a well-lit room, like here, we have some 100 lux. And a well-lit street, some 10 of lux. Even less. This is curious because we are adapted to high quantities of illuminance, and inside our modern caves that we call buildings or cities, we have very low illuminance. This is not normal, and this can cause some well-being and also health problems like seasonal depression or other things can be linked to that. But to be honest, when I have 100,000 lux outside, I can accept it because the space is huge. It's all the sky. Here, if I put 100,000 lux, no one of us will stay more than 1 second. You will enter and you will go out immediately. You will feel completely squeezed by the light. In fact, we need a lot of light when we have a huge space. When we reduce the volume, we can reduce the light. And this is a good point. Otherwise, if for 100 lux here I have a few kilowatts of installed power, imagine that we have to multiply that by 100 at least in order to achieve 100, 1,000 or 10,000 to achieve the same, that quantity of light. How we measure the illuminance? We measure that by using lux meters, which is in fact photo cells here with on the top that we call a cosinus corrector. Why? Because when the light arrives with a given angle, then in a flat detector, only the initial intensity multiplied with the cosinus of the angle is contributing. But lighting is coming from all directions, and we need to correct this cosinus incidence, and you do that by using an opaline cosinus corrector here in order to collect the light from all directions and send uniformly to the detector. An instrument like that you can find from few, say 10, 20, 30 euros. That means multiplied by 100, 4,000 rupees you can find, and you can go up to 3,000, 4,000 euros for an instrument. What is the difference? The difference that is the more expensive can measure other things, not only the illuminance, can measure color, other things that you may need, but it is calibrated. That you measure is a good value. The very cheap instrument, less than 500 euros, they are not calibrated, because a single calibration point is globally 500 euros. And normally in a metrology lab, you have to calibrate all your instruments at least one time per year and have the calibration certificate. You understand that when you buy something for 4,000 rupees, it's not calibrated, but that means you cannot measure the illuminance here, but you can say here I have 2 times more illuminance than here. In relative, it's working okay. And now I didn't have time I asked that to Amazon. There are some small USB lux meters that can communicate with your phone. I bought it for 40 euros from Amazon, and I have seen with another colleague the values that you obtain for that stuff. They are quite correct. But of course you cannot use such kind of instruments to provide metrology service. Okay? For you is fine. The excitance or emittance is the outward flux per unit of surface, of emitting surface in that time. And this emittance M is at most equal to the illumination of the surface received. You will see that at the end of this lecture, between the illuminance that arrive in the table and the emittance of the table as secondary source, you have the reflection coefficient of the surface. The reflection coefficient could be equal to 1 at the best, and then emittance equal to illuminance, but in many cases the emittance is lower than the illuminance. The luminance is the luminous intensity divided by apparent surface. That means whatever is your surface here, the ratio is only the apparent stuff. That means if you look a fluorescent lamp is circular, it's cylindrical, but the apparent surface is just a rectangle. And what you see here, more the apparent surface is small, for the same intensity, more the luminance is higher. And that, the old name of the luminance was the brilliance, the brightness. That means Smaller the object who emits light is, higher the brightness is. And as higher the brightness is, this attracts your eye. This is automatic mechanism of human being. We are looking for the brightest source. And if the brightness is higher than 10,000 candela per square meter, then you are glare, and even if you close your eye, you continue seeing a phantom image of the source, and this is a very bad point when you eliminate something. Well, give you some ideas. If we speak in candelas per square meter or nits, the sun is 1,650 billions nits. If you look the sun, as I told you, without blinking the eyes for around 9 minutes, you will be blind for the rest of your life. Thanks to our system, the eyes will blink. You don't accept to continue looking the sun like that. A white power LED, sorry, not the right button, 10 million nits, 1,000 times less bright than the sun. When you see a small LED in front of your eye, if you don't illuminate anything, you will be glared. An old incandescent lamp, clear one that you can see the filament, 6 million. The same incandescent lamp with opaline bulb, 125,000,000, because the emitting surface here is the full bulb, not only the small filament. 100 watt fluorescent lamp, 7,000. A candle, 5,000. And the moon, 3,000 nits. The moon is not glaring. You can look the moon, you will never get the impression that you are glared. How we measure that? We measure that either with luminance meters. They are this kind, or if you want that measure 1 point. If you want to measure the full space, you can use video luminance meters, which is cameras or photos that they are, or photo devices that they can get the luminance everywhere in the space with one shot. Things like that cost, say, from 2,000 to 10,000 euros. They are always calibrated, but you need to recalibrate. Things like that can go up to 20,000 euros. It depends if you want to take one frame, if you want to take several frames as function of time. You can also use your own reflex photo device, but you need to calibrate it. Few words about the basic laws. The first one is valid for point source, which is emitting the light isotropically everywhere in the space. If you have a point source here that has a flux of F, then you can find that if you go in 1 meter, you will have F over S. Say you eliminate 1 square meter surface, you will have 1 lux. If you go in 2 meters, you will have 1/4 of the lux. If you go in 9 meters, you have 1/9 of the lux. That means, in fact, for a point source, the illuminance lowers as the inverse of the square of the distance. That means if you put a lamp very far, most probably doesn't illuminate anything here. The lamp there, the light arrives up to here, but if I calculate how much light arrives here, is virtually zero since that. Of course, the light coming from sun can illuminate all the earth, but I remind you that the sun is 2,000 times brighter than any other lamp and has a huge flux. Second fundamental law, I don't understand, well, here is the problem with the different characters. Sorry about that. This is for a flat source or for an infinity size source like the sky, for example. The sky illuminated by the sun, but not the sun in direct view. Then is that we call Lambertian surface. It emits the same luminance to all direction. And if you have this kind of surface, that is usually non-reflecting surface, the walls, the piece of paper, the sky, then if you measure the luminance L in the surface, then the emittance of the surface is P time L. If I take a luminance meter and I measure the luminance of the sky, then I can find what is the emittance of the full sky in lumens per square meter of the sky. And if a part of that penetrates by the window, I can calculate how many daylight I will have on my table and things like that. Well, normally there are some relations here by disappear. That was the reason why I want to use my computer. But in any case, we'll get it in the slides after. Okay, a few words about the interaction of light and matter. Well, how the matter produce light? This is a universal principle. Well, very simply, the light is produced by atoms or molecules. But take the simple case, which is atoms. You have an atom, which is normally in steady state conditions. That means the electrons, the last electrons, they are around if I take the simplest approximation, in a distance from the core of the atom, from the nucleus, and this distance is defined by quantum mechanics principles. And we consider that when the atom is in the fundamental state, the potential energy is zero. It's a question of definition, okay? Now, if you hit the atom, if you offer him energy, you can do it by heating, by sending electrical shocks, even if you are strong enough and you can see a single atom. If you knock with a knob, maybe you can do it. Then you will offer energy to the atom, and then you can excite it. Let's say this is the electron in the potential zero, okay? I hit, and I put the electron in that distance, which is another allowed orbital, okay, in the simple Rydberg's approximation. And since I keep the electron here, well, it's okay. But there is a very important physical process who says that the stable state of a system is the state of minimum energy. Here the electron accumulated energy. Okay? The electron goes back to the fundamental state. You tell me, cheating, this is gravity. No, no. Gravity is exactly the expression of this fundamental thing. The state, the normal state, even in gravity, is when you are on the ground. If you are in another high, you will drop, unless if someone keep you there, okay? It's exactly the same thing. And then, second principle of the nature and the physics, the energy conserved. That means when my valet comes to the table, the accumulate energy to hit a little bit the table, or maybe provoke some crash on the table, I don't know. But the energy is restituted, and that means I excite an atom in a few micro or nanoseconds, will come back spontaneously to the initial state, and they will restitute the energy. But as the atoms, they can have only discrete energy levels that I will see as outcome from my atoms will be spectral lines in different wavelengths that are in relation with the atomic structure of the atom. This is the way that our friends astronomers, they are able to see that in a galaxy which is 100,000 light of years from here, They can tell you there is hydrogen, there is carbon, there is I don't know what, and they know that there is no any other elements that we know here in the Earth, because we are able, with very high resolution instruments, to see the signature of each chemical element. Okay. What happens now when the radiation enters the matter? Radiation arrive in the surface of a material, many things may happen. If the material is transparent or translucid to the given wavelengths, you may have transmission, and then you can have the radiation coming out in the other side. The only thing that this is always parallel to that, but it's a little bit shifted. Okay? Then some radiation can be reflected either in a given direction, like a mirror, or can be reflected to a diffuse way everywhere. When the light arrives here, if you see the spot, is because the wall, which is Lambertian, send the luminance to the same, the brightness to the same way in every direction. If you send that to a mirror, you will not see the spot. Only if you go to exactly the other angle that corresponds to the reflection, and then you will get the spot in the eye, and this is not very friendly. Okay? And same thing also, you don't see the beam. You see just the spot, because the beam is not diffusing in the space. And of course, the matter itself can generate fluorescence or phosphorescence. They are natural fluorescent materials. They are powered by radioactivity or different other sources. It exists also. Well, a few words about the reflection and transmission and absorption, because they are fundamental effects that we will use during this teaching for lighting. Well, when light arrives in a surface, if the surface is ideal, a part of that light will be reflected and a part will be transmitted if the material is transparent. Here, no absorption, and that means energy conservation, PR plus PT equal P in. The reflection is characterized by a reflection coefficient ρ, and the transmission is characterized by transmission coefficient τ. As we don't have absorption, ρ plus τ equal always 1. And ρ and τ is always less than 1 and higher than 0. Reflection or transmission coefficient higher than 1 or negative doesn't exist, at least in the nature. Okay? In fact, you can understand that to a different way. Here you have a beam, but imagine that you have a single photon arriving here. A single photon has probabilistic behavior. Okay? Then when the photon arrives here, he's thinking, say now I can go there or there. And what is my probability to go there is ρ. What is my probability to go there is τ. That's because ρ and τ is always between 0 and 1. Cannot do anything else, otherwise you split the photon in two. Okay? In a real case, some of the radiation can be absorbed by inside in the bulk part of the material, and then you have to add a third coefficient, which is the absorbance A, and then the sum ρ plus τ plus alpha equal to 1. Here my photon has alpha% chance to never get out from the material, but generate heat. Well, specular reflection, I told you this is general for all people. Reflection, there is only one kind of reflection, is that we call specular reflection. is a reflection kind of mirror, okay? And you know that when you look yourself in the mirror, you can see yourself inverted inside the mirror. In fact, this is also linked to fundamental physics and fundamental principles of physics. As nature like the minimum energy, nature also like the shortest way to go from a point A to a point B. Here I want to go from point P to point P prime, okay? And I have to find the fastest and the smaller way to go there. Well, if the photon arrive or the beam arrive from P hits the surface at 8, then you can imagine that the point here can move around, and you are looking for the lowest distance between P O P prime or P plus prime, and you will find that the lowest distance is when the P prime belongs to the same plane defined by P and O, which is perpendicular to the surface, and the income angle is equal to the reflection angle. This is the law of Snell. This is a physical law, but can be explained just by the fact that nature use always the fastest space and the fastest path, and the path with the less losses. However, in reality, in the macroscopic world, we have two types of reflection. One, this is the specular mirrors against diffuse. What happened here? This is diffuse reflection. But in physics, only that exists. This is just a macroscopic effect, and I will explain you why. There is the explanation. If I take the wall and I take a cut and make a zoom, then I send the 3 photons, blue, green, and red. The blue can touch the surface here. Specular reflection, the normal is here, then the photon goes there, Snell law. The red is touching here, the normal is here, then the red photon goes there, and the green touch here, the normal is here, the photon goes there. In fact, the rugosity of the surface play a very important role that my eyes perceive like diffuse reflection. The light can go to any direction if it is a real diffuse surface, but in reality, each photon follows the Snell's law. Doesn't change, only the specular reflection exists. Yes, and I think that's all for the fundamental part. Promise that was the most rebarbative and difficult part of my teaching, because if you don't understand this terminology and if you don't understand those rules and those interactions, it's very difficult to understand what will follow after. Questions? Yeah. Wait, you may need to use the micro as it is recorded, sorry.
Hi sir, actually in indoor lighting for ambience purpose, we will use red light. So in the red light LED, red light LED.
Yeah.
Normally, like in that red light, how to adjust the photometric parameters like CRI, CCT, color purity, so that we can get a good light, or like because color, if you increase the color purity, it may affect the CRI. So
yes, even if you cannot define CRI. We will speak about that in the next parts of the module. But red light, to my knowledge, is used only in night time if you want to see without disturbing your sleep. Usually we use very warm white light, and then you can define CRI and all that stuff. we will speak about. I don't give you an answer now. It's part of what we tell later. Okay? That for some people here, we have to define what is the color rendering, what is the color temperature, and this is part of what we will say later when I speak about light sources, and how this applies to lighting. It comes even later. Okay?
Yes. Thank you.
Thanks for the question, but I will answer later.
Is there any reflection of the diffuse light?
Yeah?
Like we have seen the reflection of the incident light. Is there any reflection of the diffuse light?
Yes. If you have a translucid material, the sunlight, for example, or the laser beam will hit the translucid material, and then you will have a diffuse emission. And if behind that you have a diffuse reflector, you will diffuse also the same thing to all directions. There is no difference about that. We will speak about that phenomenon when we speak about windows, for example, what happened with the windows. Okay. Other questions?
So we have seen about different units of intensity, luminance, and I generally see that we generally measure only lux in lighting system.
Yeah.
What is the physical significance of other such as candela? Do we use?
Any kind of light source you use, the flux, intensity, illuminance, and luminance are the same quantities, whatever is your light source. There is no difference between an incandescent lamp, between the sun, between a candle, an LED, or a fluorescent lamp. The quantities are the same. The values are different, and the use is different. But the physical quantities that describe a lighting system are universal. Okay? All what I said here is universal stuff. And then some more specific questions, they are not universal. They are more linked to the light source, and we will see that after. All that we see here is really universal. Applies to everything. Fortunately, otherwise, if you need specific devices for each kind of light source, it's much more complicated. No other question? Okay, then we can break for tomorrow, and we meet again tomorrow morning. This afternoon, if I'm correct, we have a demonstration. Yeah.
So today after lunch at 2:30, we will again arrange come here, and Keysight is the very good company, Keysight. So Keysight is having some solution for EMI EMC for power converters, design of GAN driver circuits, and they will provide us a very good demo for 2 hours here. They are coming offline here physically, and it will be around 1.5 hours or 2 hours. All right. And Professor George will come tomorrow morning 10. So from tomorrow 10 onwards, we will have all lectures, 10 a.m. onwards.
Okay.
All right. So all are
And normally we have the lectures in the morning, but depending on the progression, for the moment it's okay. Maybe one day we can have lectures also in the afternoon, but for the moment I cannot tell you that. This depends on on how we progress on the global program. Okay.
all right. So all invited for lunch. So daily you have to go to guest house here for lunch. All right. So all right.
Thank you.
Again come back here at 2:30.